everybody, it's Jason from Murideo, and I have a very special guest with me today, Jeff Boccaccio from DPL Labs. Jeff, how are you?
Hey, we're all doing good here in Florida, aren't we?
Yeah. We were just talking just before we went live here that yeah, it's been up here in the Tampa Bay area. It has just been pouring lately, and we really needed it,
Yeah.
rain-wise. So I'm glad to get it. And it sounds like you guys are getting a little bit of rain now too, right?
Yeah, we finally get some rain. It was getting pretty burned out over here.
Yeah.
So it's
Yeah.
hot. It's been hot.
Oh
It's been
yeah. The I think I want to say it was probably Monday or so. It's the first time this year where I've, being a native here, I've walked outside and said, "Oh my gosh, it's humid." So we're in summer now.
yeah, we're in AC now.
Yeah, exactly, exactly. Well,
Yeah,
cool. Thank you
yeah,
so much for joining. And I wanted to get
sure.
together with you because, HDMI 2.1 is no longer coming or almost here. It is here. And we're starting to see some very interesting things. Having this extra bandwidth is really cool. We're being able to do like, higher resolutions and higher frame rates and whatnot. But I wanted to talk to you specifically about testing HDMI 2.1 and also what problems installers, the everyday installer might be running into out there in the field, and maybe some of the things that we could help them with to overcome some of these problems. I know you have a really good presentation and some slides for us to go through here. So before we get started, just let everybody know there is a chat box here and a question box. So if you guys do have any questions during the presentation, feel free to type those questions in, and we will do our best to answer them. And if you guys, find this information very useful and you want to share it with your colleagues and your friends, we will have a recording of the session up on YouTube later today, maybe tomorrow at the latest. So cool. Jeff, everything ready to go on your end?
I'm ready.
Awesome. Okay, cool. So did I give a good enough intro there about what we're
Yeah,
okay,
I
great.
think you did. I think you did because you're right. We're now moving right into it. It's not like
Yeah,
it's a potential anymore.
right.
And a lot of people are not aware of a lot of the attributes that make up the system.
Mm-hmm.
And of course, we're always interested in the reliability portion of the system. Since HDMI has not been the greatest in the world historically, I'm trying to be nice.
Hey,
uh, historically with reliability, but under 48, a lot of things have changed, and they've done a few things that have really been good to help us in that department. So I think we want to run through that today. But what I want to do is the system really hasn't changed. I mean, okay, yes, we have lots of resolution, and yes, we're dealing with high bandwidths. The big difference that everyone's going to have to contend with, and many people don't quite grasp this. They're not thinking outside the box, and that is that we've really um, increased our data rate by magnitude of like 10. I mean, it's gotten very large,
mm-hmm.
and that data rate size is so big that it gets hard to control.
Mm-hmm.
And it gets hard to control not on the electronic side, but it also gets hard to control on the transmission line side. And so, what a lot of people don't understand is what happens if you don't get that entire bandwidth, or if you don't get the entire data rate.
Mm-hmm.
And you see, there are points in times where you just won't get it, at least the upper data rates. In the past, if you didn't get the data rate, the screen didn't work. It just didn't
Yeah.
operate. And now under 48, it's not that way. It's a little bit better. And so
Mm-hmm.
as long as everybody understands how it works, and we're not going to get real technical. Some of the graphs and charts I have here may look a little scary, but just hear me out. Stay patient, and you'll understand exactly what's going on. I've kind of made it a little easy so that in case people that aren't familiar with it that well can at least follow it. And
Sure.
so we're going to go from there. So let me get started. And first, my name is Jeff Boccaccio. I'm from DPL Laboratories, and we have a new system now called our 48G reference standard. That's our new test platform that we're using under this new mode of transmission. And in that platform, there's a lot of new things that happen, primarily because of the way the interface is designed. So everything has to be changed. All the equipment has to be changed. All the software has to be changed. All the procedures have to be changed. And we have to take all the things we learned in the past, primarily with the reliability problems, which is where we capitalized on, and import all those into this new system. And it was massive. It was a massive effort. It took us 2 years to develop it, to do it.
Wow.
We had to build our own test equipment, basically. We ended up, actually customizing a complete set of equipment just to do the job here that we want here. Primarily because the testing is so massive. It's so massive that the length of time in order to do a test on a particular product, if we did not change what we were doing, one cable would take an entire day.
Oh yeah, sure.
An entire day. And we don't have that kind of time because it gets too expensive for each manufacturer. So we have to increase that time. And we have to increase that with speed, with automation, and with really good software, and the software GUI, which you'll see today, that allows us to speed through all this. And we just made it really fast. So anyway, we did that, and that helped us along with all this new things with the high data rates. So let me go through this data rate here. What we call it is, we call it the operating envelope. And an operating envelope is, let me see if I can get my screen. Operating envelopes are envelopes of where you're working. And we want to prepare for this new operating envelope because the operating envelope is going to include 8K, 10K, and other attributes that are within that characteristic, meaning, frame rates, color space, yada, yada, yada. But a lot of people don't quite understand what that operating envelope really is. And so, what is an operating envelope and how does it pertain to you? Now, when you start seeing these graphs, you'll be able to understand very quickly what we're talking about with an operating envelope. So what we're going to do is we're going to go to some basic stuff that a lot of people are usually familiar with, and we'll bring operating envelopes into that area. And in the beginning, I'm going to use this tachometer, which is just a tachometer. And if you notice, the numbers are not in RPMs, they're in speed for gigabits per second.
Oh, sure. Yeah, that's cool.
Okay, so we go from 1 to 12. Right now, the needle is pointing at about 5.75. And this is the operating envelope. So when we're under Rev 20, our operating envelope was 6. That was the max that we had. And now with the new 48, our new operating envelope is at red line, which is at 12. So we have this huge area of stuff between 1 and 12. And you have to control it all. You have to pass it all. You have to make sure you get it all done with, good throughput.
Sure.
And that's what we're going to talk about today. So let's look at something really easy. And this first graph we're going to show you is just what the system looks like. We call it the system environment. We have to look at the entire system. We can't look at if we're testing a cable, well, that's fine, but the cable works with a system.
Right.
And you've got to bring the system in because they too have their little innuendos, as you might say.
Yeah.
And they're all different. And all the guys out there that works out there in the field has to work with these systems. And one of them in particular, of course, is our cable. And the cable is the more blamed product in the world.
Sure.
And it's blamed because of many reasons. One is that, there's a lot of not so good products out there. There's a lot that just go out there. They don't go through any compliance testing. They don't go through anything. They basically slap these things together and they throw them over the fence. And then they send them out to the public and sell them. And that's okay. Some of them accidentally come out pretty good, But
happy accident.
But then a lot of the better named products usually will go to manufacturers that have some background in doing this properly. But again, we're dealing with an environment where the cable sits there and basically the cable doesn't know. It really doesn't. I mean, you're taking this foreign product and you're connecting up 2 devices, and this is a simple system. This is nothing. I mean, this is a basic system, man.
Sure.
So you can imagine what happens as you start getting involved with matrices, and distribution systems, and things like that. So let's look at what this little cable's got to contend with under operating envelopes. And the first envelope we're going to look at today is audio. Everybody knows audio. Audio is, if you don't know audio, man, you really got to get your homework done,
This is Audio is the reason, or whatever however you'd like to word it. Audio is the reason I got into this business. It's a lot of fun.
Sure.
It's a lot
Even
of
for
fun.
me.
Yeah.
Even for me. I mean, I was a two-channel guy way
Yep.
back in the late 60s. And, as things progressed, we moved up into video. Now, I had
Sure.
always had a passion for video, but I got into audio and I stuck with it until it finally transferred over. But when we look at operating envelopes, what we're looking at in audio is a case where it goes from 0 hertz out to 20 kilohertz.
Mm-hmm.
So we have a 20 kilohertz or 20,000 hertz, so 20,000 hertz of information. I'm going to use information. So let's change it into a graph. Let's just look at it this way. So now we've got this graph here, and let's just shoot a line. And this is a typical flat response of an audio system.
Mm-hmm.
And you got to have this. Now, inside that response, there are features that you must get. When you buy an audio system, you expect to get these features. And one feature is you expect to get a really good high frequency response. And, if you do the job right, you'll get the horns and you'll get the cymbals, you'll get the definition of what goes on in the audio. And if you have enough low end response, then you're going to get the bass, you're going to get all those things that happen on the low end. But in some cases, maybe you don't quite have that response. You have a dead tweeter or you have a crossover network that's beginning to go sour on you. And things happen. So what do? They can bring in equalizers.
Mm-hmm.
They can change the curve, or they can just use their bass and treble control to do it.
Yeah.
Well, these are known in the industry, and when you get into the upper end industry, these are known as what we call as tilts. So a treble is a treble tilt. So we're tilting it upward in the high frequency response. We can also tilt it down if we wanted to. And the same thing happens to the low end. In the low end, we can tilt up or tilt down. So we can basically modify the way the system sounds by changing the tilt on this. But the whole idea is if by the time it reaches the human ear, as long as you have a flat response, the system should sound as near to real as possible. And that's what everybody's looking for. Everybody's looking for the same thing, right? Okay. So that's the audio side. So the spectrum is from 20 to 20K. So now let's move, let's up it up at one notch. Let's move to analog video. Now this goes back into NTSC, and let's look at what that envelope looks like. And that envelope looks kind of like this. So now, if you look at the very left-hand side of the screen towards 0, you'll notice that our little audio over here just got crunched down.
Just a blip.
Yeah. I mean, just a little blip, right?
Yeah.
And our actual bandwidth at NTSC was about 5 megs. So we have a 10 meg bandwidth, and this is what our our video would look like. So now this is again a relatively smooth curve. It's pretty okay, but in this case, if we don't have the upper frequency response, we lose definition, we lose sharpness, and in many cases, you can actually look at sharpness controls, and what they are is basically another tilt, where they're tilting up the upper high frequency response. So that's an operating envelope. So in this envelope right now, we've got NTSC and we've got audio, which is way down on the bottom. And then, of course, we also have audio modulating on top of the NTSC, and actually it's done in frequency modulation. But you can see how this envelope is beginning to get large. And, excuse me, transmission lines, typically copper, they try to be as linear as possible, but as you go up in frequency, they don't. And in order to keep them somewhat smooth and linear throughout the response curve, it's a challenge for any cable manufacturer, especially when it comes down to the raw cable manufacturer itself. So let's move out of one more notch. Let's look at the RF spectrum. Now look what happened here. Again, the audio is crunched even more because now our total envelope is a gig, so it's 1,000, right? It's 1,000 megs wide. So audio is crunched down to nothing, and look what happened to our video.
Yeah, it's almost gone.
Our video is it's almost gone, right?
Yeah.
So as the operating system gets bigger in envelope, so does the curve. So now you've got to have this curve that goes between these two marks, because under terrestrial broadcasting, they've got to go between channel 2 and channel 83. And this is when the guys were running coax, right? Or for
Sure.
cable. They're running
Mhm.
coax to the homes, and you're running a curve that looks something like that. So, these curves, again, have to be as linear as possible. Otherwise, you may lose a few channels.
Yeah.
I mean, how many times have you put a system in, you put distribution in throughout the house, and you find out that the upper channels are snowy?
Yeah, sure.
And they're snowy because the transmission line is not providing a smooth response out to the end of the envelope. And so, how do you fix that, Jason? What do we use? Guess at this one. This is easy.
An amplifier or a booster or something along those lines.
Or a
Or
tilt.
Right?
So we would use tilt in most cases at UHF, and those tilts could correct those problems that we had in the RF spectrum.
Mm-hmm.
So again, as it gets bigger, it gets harder to do. And coax, you think about coax, people come up to me all the time, they say, I don't know why we're going through all this crap with HDMI wire. We should just use RG6.
I hear it all the time.
And, and you say, how big that wire would be?
Yeah.
At RG6, you need 2 for each channel. You got 4 channels. I mean, this thing would be, it'd be
Right.
a football, right?
Right,
and,
yeah.
And they're already complaining about 24 gauge being kind of clumsy, right?
Yeah, sure, yeah.
So it's very hard to give you a smooth response curve when you get into real small gauges. And under RG6, I mean, that'd be beautiful if we had that. And even that, when you look at a spool of 1,000 feet, 1,000-foot spool, they give it to you and how many dB you're going to lose, per gig.
Right.
And you'd be surprised you lose a couple of dB per gig even with that. And a couple of dB when you get to 3, you're doubling it at that point.
Yeah, sure.
So you gotta keep this thing as linear as possible. Okay, so let's move up to the next notch. Now we're moving into digital video. And here's our first HDMI Rev 1. And this is going out to a 1.5 gigs. So now look at down on the left-hand side, everything's getting crunched even further. Mm-hmm. And of course, this is our response curve. And this was the easy days. This was the days where we only had 5 gigs to deal with overall aggregate.
Mm-hmm.
And even then, that's when the big problem came, because nobody was used to doing this. Cable manufacturers weren't used to making this. Many people didn't understand what the test environment should have been. And a lot of things didn't work. And not necessarily because of the video either, by the way. A lot of it has to do with the information channel, which is the DVC channel. And that channel rides, of course, the encryption.
Sure.
And the encryption was not working half the time. So it was nothing but just a litany of problems that occurred.
Yeah.
But what we didn't need is we didn't have to compound that with an operating envelope problem. But they did it. This little envelope looks pretty good, and we didn't have to do anything. We just hooked it in as long as it didn't go real far. Mm-hmm. So, what could we do at that point in time? Remember, at that point, it was standard cabling. Mm-hmm. And, typically you get 4, 5, 6, 7 meters. It was good. But then Rev 1.3 came out. And here, I'm going to go back to a couple of features. Under Rev 1.1, we got 720p, mm-hmm. and we also have 1080p 60. Okay, so those are features that we received under Rev 1. And we want to hold on to those features because that's how it really did look very good. But then came, that's where our RF spectrum squeezed down to.
Oh, sure.
And those are the old ones down there. But then as we moved into the next revision, we went to 1.3. Now, under 1.3, you can see what happened. 720 got pushed down, 1080p got pushed down, and now our total per channel number is 3 gigs. Mm-hmm. So we basically doubled it, right?
Yeah, sure.
We went from 1.5 to 3. So
yeah.
In one revision, right?
Yeah.
And you're going to find that in all the revisions we doubled it.
Yeah,
it always
sure.
works out that way. So now, as this thing gets bigger, the transmission line has to be very, very well received. So what did they do? They changed the wire from a standard to a high speed. That was when they made the Category 1, Category 2 changes. Mm-hmm. And in the high speeds, a lot of people did high speed by just increasing the gauge. And then other people did it by actually improving the capability of the cable itself. But no matter which way you got there, you still had to have some curve. And what was it going to give you? It was going to give you something like this.
Mm-hmm.
So here you got the high frequency roll off here. You can see that now. And of course, with this working right, we're going to get more features. So now we have 1080p 60. We got deep color out of it.
Mm-hmm.
We got 3D out of it. We got 4K out of it.
Mm-hmm.
So this is all good stuff. Now we're really getting some features that consumers really want. But it didn't work real well, especially at longer lengths.
Yeah.
And when I talk about longer lengths, I'm talking about 3, 4, 5 meters. It didn't work very well.
I would always sort of try to limit those systems to really 5 at the most. In those days.
Yeah, absolutely.
Yeah.
But as we moved into custom though, 5 wasn't enough.
No, not even close.
It's 15. That's 15. So give me a break, right?
Yeah.
And so HDMI realized this, I think, and they came out with a 1.3a. And under 1.3a, they introduced, guess what? Tilt.
Yeah.
They offer tilt, and the tilt is inside the display.
Mm.
So now the TVs had a little bit of equalization, and they were able to bring the cable back up to a number where we can get out to 5 and 6, and maybe even 7 meters.
Mm-hmm.
That was a big deal back then. That was a really big deal. But you see, it's more vulnerable as we move further and further out in the envelope.
Mm-hmm.
Okay, so now what do? Now we're going to go to 2.0. Everything gets pushed down. Everything we talked about in the earlier time of the presentation, practically gone. 720p is pushed way down there.
Mm-hmm.
Our 3 gig deep color is in the middle, and now we're up to 6 gigs. So it's getting pretty dodgy now as we start going further and further out, and now the curve really looks funny. So these peaks and valleys are okay as long as they don't deviate too much.
Sure.
Because in digital, it has a little bit more wiggle room. What I mean by that is that it can become relatively stable as long as you're within a particular envelope. Mm-hmm. And this is more, actually, it's analog. The actual data that comes to those HDMI cables are actually analog.
It's still analog, yeah.
It's still analog. So we have to be sure that those eye patterns that we use to measure these with don't change vertically. Mm-hmm. And if they do change vertically, they can't change by more than, 700 millivolts. That's very small. Mm-hmm. So you got to be very careful with that. So what does this give us? It gave us more features, didn't it? More to sell. What made customers buy more. Yeah. This is all a good thing. So now we got even more goodies. We got 4K 60. We got 4:2 color spacing under 60. We still have our 3D. We still have our deep color. We got 4K 30, and we even got HDR.
Woohoo!
So, wow, this is really great. We're really getting a lot out of this envelope. Well, it didn't work that well because HDMI did not prescribe a new cable, did they? Their prescription for this was to use a high-speed cable. Mm-hmm. The one that was made under 1.3. So they rolled off at the end, and you didn't get the distance you could get. And again, the guys in the field, they got to turn corners, they got to go long ways, they got to run up the conduit. They don't want to replace them again. What are they going to do? So of course, what does HDMI add, Jason?
Let me guess. Tilt.
Tilt, absolutely. They added more tilt. And the tilt brought it back. So we're getting, I can tell you right now, we just tested a client's cable. He made an 18 gig cable, right? Which is 6 gigs per channel. Mm-hmm. 10 meters long. Passive. And it made it. It's 24 gauge.
That's what I was about to ask, yeah.
It's 24 gauge, but it's got some special alloy on it, which they use. They plate it in silver. They do it in twin axe. There's all kinds of little tricks you can use to get there. And it costs a lot to do that. But it goes to show you how technology has adapted to this huge envelope of 6 gigs. Well, it didn't take too long in 2017, and they went and announced that 48G was now around the corner. And 48G really changed things.
Oh yeah.
Because now, look what happened here now. Our operating envelope got huge.
Mm-hmm.
So look way down there. You see channel 54 way down there for
Yeah.
channel 2.
Yeah.
1080p is really low, and
Sure.
even 4K 60. So 6 gigs in the middle. And now what does this new one offer? This new one offers a very unique transmission line now. And remember, this is copper. We're not talking fiber yet.
Yeah.
So now with this copper, how far are you going to go with this? I mean, really, I remember at the announcement at CES, I was there, and they got up there, and the HDMI got up there, so I'm talking about this. And finally, they had a Q&A, and their technical guy got up there, and one of the reporters asked a question saying, well, what about the cable manufacturers? How do they know what they're doing here
Mm-hmm.
with 48? His comment was really incredible. Incredible comment. I'll never
I can't
forget
wait.
it.
I can't wait to hear this.
Yeah, this is good. Well, they'll have to figure it out.
We'll fix it in post.
I mean, the guy did that with his orange pants.
Yeah.
You know how they use their orange pants?
Oh yeah. Oh yeah.
And I'm sitting in the back saying, oh my God, this is not good PR. And of course, everyone's bumbling, saying, we're just about making it for 18G. You want us now to go to 48?
Right.
And what are you looking at in lengths? Maybe what, 2-3 meters? I mean, come
Mm-hmm.
on, give me a break,
Yeah.
right? So we knew it had to go active. I mean, it had to go active. There's just no way
Mm-hmm.
out of it. And so in order to do that, we now have to get all these new features, right? So now we've got 6 gigs, 8 gigs, 10 gigs, and now all the way to 12 gigs per channel. And you see there's more features. And
Right.
remember, every one of these features also includes everything you see under 4K 60. So
Oh
like
yeah.
AV
It goes back. Yeah. Sure. Sure.
goes back. So now when you get these consumers that hear about 48G, they say, my God, I want 8K. I want 8K. 8K. Give me 8K. Well,
Mm-hmm.
they announced this thing in 2017, Jason.
Right. Right.
It's now 2021. It's just starting out. So,
Mm-hmm.
for all these years, people have been screaming, when am I going to get my 8K? They weren't even close to doing this.
This all sounds familiar when 4K launched. It was a very similar
Yeah.
conversation. Very
Oh,
similar
absolutely.
conversation. Yeah.
And in fact, I can remember when they announced in 2013, and I can remember them announcing it. And guess what? They weren't even producing 4K 60.
Yeah.
It was only 4K 30.
Right.
4K 60 with low color space. So it
Mm-hmm.
wasn't until HDR came around before they actually started getting to the full 18 gigs. So now we've got this huge bandwidth. Look at the response of the cable. I mean, we're going to have to do something about this. So what does HDMI do, Jason?
Is it a 4-letter word that starts with a T and ends with a T?
Yeah. They add tilt.
Actually, real quick, I do have a question. Just based on the graphs you're showing us, is it safe to say that the higher the frequency, the more severe the roll-off is at the end? Is that a good observation?
Yes.
Okay.
I'm sorry. I thought maybe I brought that up before. Yes, the higher the frequency you go, but the larger the envelope, the higher the frequency. The copper is not. This is why we use fiber, right? Copper can't go that far.
Sure.
So it just attenuates to hell. But in order for the copper to work, even over short distances, 3-4 meters, we need tilt. So they added tilt. Well, that's a funny looking tilt, isn't it? I wonder why.
Yeah.
I wonder why. There's a reason for this, And the reason is because the peaks and valleys that occur throughout the interface, if you don't have it all, you're going to start missing things.
Right.
Like if there was a really big valley at 6, you're going to lose all those 18G properties.
Mm-hmm.
See, I mean, remember, it's just like when we went back to audio. If you didn't have the high frequency, you'd lose the sharpness, you'd lose the definition, you'd lose the treble, right?
Sure.
It's the same thing here. You have to get the entire envelope. So this is the tilt they gave you. But that envelope is so big.
Mm-hmm.
There's no way they're going to do this with just one equalizer.
Right.
Instead, they used 8.
Whoa.
Right. Now they don't use all the 8; they just use one out of the 8. And so
Is
now
is
the team. I'm
it,
sorry. Go
sorry,
ahead, Jason.
is that for like redundancy or headroom or?
It's for no. It's for envelope. It's
Oh,
because
okay.
they don't know if let's say, cable may make it to 10, but what does it do at 6?
Gotcha. I gotcha.
And what does it do at 12? They could be all over the map. And HDMI knows. I mean, they've been in this ring for a long time. The
Hmm.
cables that come out of China, which is where most of them come from, not all of them are exactly high speed.
Sure.
And a lot of them slip through, and the poor guys in the field are buying them, and they have all this propaganda on them, saying that they can operate underwater. I mean, come on. I mean, you got to be smart. You got to be real, especially when you're out there doing the system. You're in the
Right.
front line,
Hmm.
and you can't afford any time to screw around. So what they did here is, which is a very good idea, by the way. I got to give a lot of credit to this. They gave us several equalizers so that now the television set makes a decision. So as the cable gets plugged in, the TV will sit there and say, okay, let's see, this cable is really not doing that well. I'm going to give it 7. Okay, so 7's going to be pretty strong.
Hmm.
So if I had a cable that did 7 and another cable that only used 2, hmm, that would kind of tell me that the cable that only used 2 is probably better. It doesn't need that much correction.
It do, is there a possibility of overcorrecting?
Absolutely. This is why it's got to know how much to give it and how much not to give it, and
Hmm.
that's where fiber comes in. Because, and I'll get into that in a minute, but I
Oh,
mean,
sure.
but yeah, I mean, you can oversaturate, and
Hmm.
that happened with the Redmi products. In fact, all of the S7 products in the 18 gig time, they were having trouble out there in the field, and a lot of that was due to saturation problems. It
Mm.
wasn't really their problem, but it was their problem because they were delivering a relatively good signal to the input of the television. And of course, the
Hmm.
television thinking it's going to have an attenuation coming in, and it had no control. That tilt back in Rev 2, it was on all the time. There was no control.
Oh, okay. It was either all or none, yeah?
Yeah, all or none. And so but under 48 now it's smart. It can tell. It'll say, okay, this one needs a 6, this one needs a 7, and it's even better than that. It's discrete. They actually do it by channel. So
Oh,
you can have channel 1 doing a 6 and channel 2 doing a 7, and it allows the display to adapt itself to the cable, which is absolutely spectacular because
yeah.
it alleviates so many problems for the installers. I was thrilled to see this. I was thrilled to see this.
Yeah, it sounds very, very clever. Very clever way of
Very,
doing it.
very clever, very clever, very clever. So, but things kind of are not always perfect. And I think HDMI realized they aren't going to be perfect. And so HDMI knows that there's also losses within the system.
Hmm.
We've known this for 10 years. There's
Yeah,
always
that's nothing
losses.
new. Yeah, sure.
And when you look at the perfect world where you say, okay, this cable is going to pass X, yeah, what happens if there's little losses in there you don't know about?
Yeah.
And these poor guys that are out in the field, they're dealing with losses every day. They don't even know it.
Hmm.
And so it's up to us to make sure that as a testing agency, we've got to be sure that you've got, the chutzpah to get out there and get over those losses.
Hmm.
And you've got to look at where these losses will appear. They appear in the source,
Hmm.
they appear in the display, and of course they appear in the cable.
Absolutely, yeah.
And they'll appear, and then there's tolerances. There could be as much as 10% tolerance
Whew.
between products as you start building tens of thousands of these things.
Yeah.
And then you got the connectors that back in the day they were all soldered by hand. So and how did they test them? They plugged them into a television.
Yeah. With nothing in between.
Whoop de doo.
Yeah,
I mean,
sure.
that's going to tell you a lot. So it was not a good move. It just wasn't a
Hmm.
good. So this is what they have to play with, is all these losses. So let's look at some of these losses. Where do they come from? Well, here's printed circuit board, typical for any kind of source product. And you can see here that that little red circle I've got there shows you the channels coming from the HDMI connector that goes into the output stage of the HDMI transmitter. Now let's just look at this a little closer because there's losses here. So we're gonna zoom in here.
Oh, good, yeah.
Now you can see 8 traces. Remember, there's two traces per channel, and 4 channels, so we need 8 traces. And just in this one board, and I don't think it's more than, I don't know, 6 to 10 millimeters, you can lose up to 2 dB.
Oh, wow.
And yeah, because the first thing, the trace is very small, they're very thin, they've got to be balanced, they've got to be trace equalized. The board material has to be matched to the impedance, and it's got to fit into the TV, and it's got to be cheap.
Yeah, it's got to be. I was about to say.
And so there are better materials in the fixtures we use here in the lab. We designed our own fixtures in the lab here, and we use material called Rogers material. And the Rogers material, most materials FR4, we use Rogers material, which is a lot more money, but it's got a lot more bandwidth to it. So the operating envelope of the Rogers material is very, very big. But here you can see what happens here. But this is good. This is all very good. What happens if you go to a TV set that has maybe here's a good one. I snapped an eye pattern on this.
Oh, cool.
This is the eye pattern snapshot of this particular output. So I literally went right to the pins of the HDMI connector, and you can see, look at channel 4, which is the one on the bottom right.
Yeah.
Look how much smaller it is.
I was about to say, yeah, it looks much smaller than the others.
Yeah, so the little grayer around the pink is the mask margin. So, it's called the mask. The little thing in the middle is the mask. We don't want to touch the mask, right? But how much distance do we have between the mask and the actual signal? And you can see in channel 4, it's getting pretty close.
It's, yeah, I bet if we zoomed really far in, it's probably almost touching.
Well, it's touching, but that's the mask margin. It still has a way to go to get to the pink.
Gotcha.
But with Jason, we're only 10 millimeters away. I mean,
like what do you expect?
And the other thing that people have to realize is that when you get to 12 gigs, you're not going to get all these channels exactly the same anymore.
No way. Yeah.
There's just no way it's going to happen. So again, that tolerance level, you got to watch that tolerance level. Okay, let's go to this next one. You're going to love this one. Okay, now we're gonna go out to 5 inputs on a TV set.
Oh, cool. Yeah, here we go.
Okay, so that big chip in the middle, that's turned upside down, that's the HDMI receiver. It needs, since there's 5 inputs and there's 4 per input, it needs 20 pins to take the input, right? So if you look at input number 1, which is here, well, that's about as long as you can go.
Yeah. There's a distance thing going on there.
That'll probably be the worst input in this TV set.
Sure.
And what a lot of guys do is they go and they use the display and they think, oh no, HDMI 1, it's got to be first. In most cases, it's the worst.
Maybe, yeah.
The chipset is a 100-pin package, and it's going to be square. So you gotta make turns. So you look at that, and then you look at number 2. Here's number 2, and number 2 is a lot better. Number 3 is actually the best one out of the lot.
Yeah, it looks like the closest or shortest one.
Yeah, and then you look at 4, which is getting dodgy, and then 5, you're out in the back 40 now.
I'm sorry, just for my own curiosity, there's like 2 maybe brass or gold bars surrounding input 1. Do you recall from this specific board what those 2 things are?
Yeah, those are mounting boards. Those are mounting pads. I see.
That's just to mount it. Okay.
Yeah, they ground plate it, and it's just a copper flash.
I was curious because if that did have something to do with power, those being that close to the traces, if that potentially could,
Yeah. Well, if they were floating, there could be some residual noise on there too.
Yeah, sure.
So, let me go. I'm going to lose time here. I'm sorry.
Yeah.
So what they did is they got smart and they said, okay, we know this industry. We know it's not going to be a perfect world. So they added a little thing called link training. And it's been around for a while. It was in Ethernet. It's in DisplayPort. It's a really good deal. It's a great thing for the guys in the field, kind of. So here we have our system again. And notice we have no signal found on the TV set. And the system's on, it's looking for 48G, but it doesn't see that. Well, link training does this. The TV set will send a signal back to the source. And it'll say, hey, buddy, I can't see this.
Yeah.
You need to help me out here. So it says, it turns around and says, oh, okay, I'll fix that for you. And it goes and sends back the correctness signal and drops the data rate to 40. Okay? So now it's still no signal. So he says, oh, no. And so it goes back again. And it says, hey, I still don't have it. It goes back and says, okay, drops to 32. Still don't have it. HDMI knew this is coming. They put this in here specifically for this. So now it's going to go back and say, okay, here we go again. We're going to drop it down to 24. Boom. We get a picture.
Now you got a picture. Yep.
Well, so now the installer can walk out with a picture. Wow.
Yeah. It works.
Yeah, there's only one little problem there, and that's this. We basically lost this much.
Yeah, right.
Of what the guy paid for. All right, so now what happens with link training? It's pretty much guarantees functionality. It automatically takes control. You have no control over this, the operator, and it limits system's ability to support its real true image. You're not going to get it. So who owns the liability for this image reduction? Well, what happens if the customer, which you know is going to happen, the display guys are going to start building on-screen displays that says, I'm seeing 32. And the owner says, that's not what I paid for.
Right.
I paid for 48. I mean, someone's going to be in poop here.
Yeah.
And I can tell you, it's not going to be me.
Yeah, it's not. Yeah.
And the installers have to be aware of this. They have to know that it may work, but man, if that guy finds out it's not operating at where it should be.
Yeah.
And so, so we decided to get into this thing about 5 months ago, and we did a lot of work on this, and we came up with a new procedure in testing called true image testing. And what this does, it allows us to use additional routines and design to avoid link training. We want to make it so the cable never enters that link training area. We add stress test analysis into the cable. That means that we make it worse before it goes in.
Yeah.
Basically making it so that we can artificially have the cable see what goes on there in the field, because that's what it's going to see. It's not going to be in the lab. It's going to be in the field. And this took months to run these routines and write these algorithms. So if you look at these things, there's induced stress in the source. There's induced stress in the sync side, and of course we add more stress into the cable. So it determines the cable's dynamic range limits. So we know what the cable's headroom is going to really be under stress and under very, very adverse conditions. And then we use our historical case studies for 10 years. No, we know how this works.
Yeah.
We've been here before.
Been there, done that.
Then they're done that, and we wrote those routines accordingly. So it reduces link training data reduction. So now if the unit went through image testing, the odds of it falling into the costs of link training is minimized. And the guy won't have to worry if the thing isn't working. Here's an example. Here's an eye pattern. Now this is, I know a lot of guys maybe don't know what this is, but this is what we use.
Maybe a quick and dirty explanation, just in case folks watching aren't quite sure about eye patterns.
The eye pattern is basically what you're looking at is square waves that are basically inverted. So you have one going up and one going down. But as you get faster and faster in speed, they begin to curve. They begin to get a little curvy, and they resemble a human eye. So they call it an eye pattern. The vertical amplitude on this is what the data strength is. The horizontal is what I'm going to use. It's actually jitter, and it's where clocking begins to go crazy, and it starts moving so much it can't discern whether it's a 1 or a 0.
Mm.
And there's many more things in this. Now, we
Oh,
could do
yeah.
that another time.
That could
There's
be a
a
whole, yeah, yeah,
Oh yeah, I mean, what this tells the operator is a story, a
yeah.
very long story. But just for today's discussion, here we have this really nice eye pattern, and the eye pattern has attributes. But what we look for in true image testing is we look for higher, a much higher demanding signal limits. We need a nice, big, robust signal limit in order to make sure we don't fall into that category of the link trading. We have to watch the jitter, so we induce the jitter. You can see that little line, that
Mm-hmm.
little blue line under the arrow.
Yeah.
That's induced jitter. And what we try to do is we try to make that jitter, force it to hit the mask, which is the pick area.
Mm-hmm.
And it's got a long way to go.
Sure.
So this particular device under test is doing extremely well. Then we also look at crossing percentages, which many people don't look at, and we look at this very carefully because
Mm-hmm.
that crossing percentage, it could cross higher and lower. So it could cross 25% up, 30% up. Well, once it does that, the negative going waveform gets distorted, and it adds to link trading problems. We're going to go into link trading. And also, we have to be concerned about noise.
Mm-hmm.
Again, you don't even see these noise levels on HDMI specifications.
Sure.
There's no crossing percentages, and they just don't do that. And then what we do is we take the eye height ratio, which is the ratio of the height to the rest of the system,
Mm-hmm.
and that's going to compute into a number, and that number has to be below X.
Okay.
And if it makes it below X, you have passed true image test.
Got it.
And that's where the guys have got to think. They got to be secure in what they're doing.
Mm-hmm.
And then here, this is actually our test equipment that we developed, and the equipment is actually made for manufacturers.
Mm-hmm.
So the manufacturer can snap 4 of these eyes on the assembly line, and they can do it in less than 10 seconds.
Oh, cool.
So yeah, so now they don't look at TVs anymore. Now they're going to look at 4 eye patterns. The operator, there's a flag up in the right hand corner that says pass. Right?
Yeah.
They don't have to think. They can look at it, and then if it doesn't pass, they can look to see why did it pass.
Mm-hmm.
Number 1, number 2, or if they want to get really esoteric, they can teach themselves how to read them. But
Yeah.
now they see exactly what each channel is doing.
Mm-hmm.
They know exactly what the cable is doing, and so they can go through thousands of cables now without just looking at a TV set anymore. Can you imagine if they used a TV set, Jason, under link training?
Yeah, it would.
They could be passing cables out there at 24, 32. Oh, it even drops on the TMDS.
Yeah, yeah. And it's got 48 splattered all over the packaging.
All over the place, right. So
right.
Anyway, that's what we do at DPL. And the whole idea for link for true imaging is for reducing the influence of link trading.
Sure.
That little diamond thing on the bottom is the actual mark that each cable will receive that goes in the package. Sure. And then below it is, of course, the coding so that there's no counterfeit.
Yeah.
But that's what I wanted to get at least through what operating envelopes look like. Mm-hmm. And so the guys know when they're pulling that stuff, know what you're pulling, understand the envelope, because your customers are going to want all of it.
Mm-hmm. Absolutely. When I have a question about the eye diagrams.
When go back to it.
Yeah. Just to so when I look at it, I know what I'm asking at least. Yeah. So that's an example of good, right? That's a very nice looking eye diagram.
That's excellent.
At what point? I mean, I know we talked about especially the middle eye, that being as big and wide and as tall as possible. At what point, looking at an eye diagram, at what point is it considered like a total fail? Would that be completely closed or barely open, or? And I'm sure there's some numbers and amplitudes and things like that are in the graph that'll really tell you.
If it's really bad, it's just no.
Gotcha.
It's just a one big blur, right?
Yeah.
And we see a lot of it.
Mm-hmm.
I mean, we had a series of products coming yesterday for pretest because the manufacturer made their cables up. They wanted to see if they were going to make it through.
Mm-hmm.
And they sent in 3 samples, and out of 3 of them, 1 of them had 1 channel that was all snow.
Oh wow.
So what that tells me is that they can do it if they can produce it the same every time.
Mm-hmm.
But clearly that one cable, that one particular channel, and it was channel 2, didn't make it. So, but what happens is that basically the way this works is this. Can you see my cursor?
Yes.
Okay. If you notice, my cursor goes around the top of the eye here.
Mm-hmm.
So this gray area here is, I'm going to call it the safe zone.
Yeah.
So, that's kind of like, oh, yeah, man, that's really great. That's safe zone. And so up here in the top, you'll see it says 51.6.
Mm-hmm.
So that's over 50% safe.
Oh, good.
This is really good. This is really doing quite well, right? But as the eye gets smaller, which they do, I mean, they get so small, it's just all blue in the middle.
Sure.
But as they get closer and closer to the actual mask, this number is going to go down.
Right.
And the lower that thing goes, the more susceptible it is that's going to fail. Well, again, the whole idea is you've got to get all 4 channels that are above that mask.
Mm-hmm.
And I'm going to tell you, it's going to be a challenge for a lot of these guys. And just to talk to you just a second about fiber.
Mm-hmm.
Fiber comes out, and they're good. They come out of there, and they put out a really robust output, but
Mm-hmm.
it's too much output because the 8 equalizers have to handle this.
Mm-hmm.
So we had one fiber that came in one day. This is really incredible. It did really well. At least one channel did well. But 2 of the channels, one of them was using an equalization of 1, which meant it did really well. And another one was using an equalization of 7.
Oh, wow. Almost all of them.
Yeah. And so what you do in this case is you turn all the equalizers off, and you want to see what the raw data looks like.
Mm-hmm.
Well, I'm telling you, you should see the deviation in these fibers.
Wow.
It's unbelievable.
Is that maybe due to like the purity or the clarity of the fiber material itself, or what could you blame that on?
Look, there's so many things. Remember,
There's a
that
lot,
operating
yeah.
envelope, it gets big. The biggest thing is going to be consistency. So in other words, if I took 3 of those and they all did the same thing, I'd say the module's bad.
Right.
The guy whoever did the artwork on the module screwed up.
Mm-hmm.
And we see that all the time.
Sure.
And as we do more and more events like this, we'll start going through some of those idiosyncrasies. We'll start diving into fiber. We'll show you what other attributes that cause these problems are, and ways of fixing them,
Mm-hmm.
and ways of fixing them in the field. And the nice thing, I don't know if you know this, I don't know if I told you about this, but HDMI has just increased their current allotment. So
Oh, no, we haven't talked about that.
Yeah, they used to only have 50 mils of current available. So of course fibers would never do that.
Right.
Typically these things are running between 50 and 100 mils. So there's just no way it's going to work.
Mm-hmm.
And the only way they work good is if you had added some external power to them.
Right. We've
Some
seen.
people did, and some people did, and some people didn't. And it's because depending on who made the source, like I saw an LG, like a $150 LG player come in, and
Mm-hmm.
it had a source current of almost a half an amp.
Yeah.
That's 500 mils, right? That's a lot.
Mm-hmm.
And then we got another one in here, a real nice one. I'm not going to tell you who it is, but it came in here and it was only doing about 100 mils.
Mm-hmm.
So when you start getting these different fluctuations, guys would plug them in and say, "But look at it, worked. It worked." Yeah, it may work there.
Yeah. Right.
And maybe only for that particular source. Remember, the power is coming from the source.
Mm-hmm.
So you're better off adding extra power. You're better off. But HDMI realized that finally, after 4 years, we're going to need active. And so they upped that. They gave it a really good name, Jason. I got to give these guys credit. They've got class when it comes to naming things. They call it cable power.
Cable power.
Yeah, that's it.
I was expecting like a ultra something, or they always use these funny words. But hey, cable power, that's cool. I'll take it.
Cable power, right? But it's nice because they're gonna guarantee 300 mils.
Oh, good.
Well, that pretty much lets everybody off the hook.
Yeah, right.
And now you just got to figure out who's doing it.
Yeah.
Right? It's only going to come from the source. That means if you bought a Marantz or a Denon or something like that, you'd have to either look at the box or ask the company and say, "Does this have cable power?"
Mm-hmm.
And for 90% of the time, the guy's going to say, "What's that?"
Yeah, right. Yeah, yeah.
But that's a new one. So, but there's things to talk about that we could do on other episodes.
Sure. And is it one of those matters of you plug the cable in, it's dodgy, maybe you don't get a picture, and all of a sudden you plug in a little power module to it and boom. Is that related to the cable power? If the devices itself aren't doing it, aren't we putting
Yeah,
power into the cable?
that's right. We're putting
Yeah.
power back into the cable, but you see, not only is it powering the active parts in there, but in some cases it also provides insurance for other portions of the interface that require that same power.
Mm-hmm.
See, like the DDC line that controls the HDCP, it operates off that same power.
Right, right, right,
So
right.
if the power is not there, even if you came in with this fantastic chipset that did a fantastic job on 4 channels of iPads, let's just say it may not still work because
Right.
if there's not enough good clean power going down to the DVC channel,
Mm-hmm.
well, the unit's not going to pass HDCP. So
Could it? Oh, go ahead. Go ahead. Go ahead.
it just people don't understand that one attribute of the interface can very easily affect another one.
Sure.
And they'll say, oh, well, the reason why that happens is because you didn't turn the power on in the right sequence.
I've heard that. Yeah.
I
You
mean,
shouldn't have to.
do you really think? I mean, we've got a rover on Mars, right?
Mm-hmm.
We got a helicopter on Mars.
Yeah.
These guys are automated. Do you think in a million years that somebody at HDMI wouldn't think that somebody wouldn't know exactly the right sequence?
Right. Yeah. Yeah.
And if that is the case, shame on
Yeah.
those hardware companies. Shame on those hardware companies.
Could you imagine setting up a system for an end user in their home, and you finish up everything and everything's working, and you hand them a sheet of paper and you say, okay, when you turn the system off tonight and you come in tomorrow and fire it back up, you have to turn things on in this order. Their heads would explode, and I wouldn't blame them because even I wouldn't want to do that. I mean, that's crazy.
No,
That's
I can
nuts.
see the wife wanting to see her 1 o'clock soap opera. She's 3 minutes before prime time, and she's trying to figure out how to do the sequence.
Yeah, she's like, is it the cable box first? Is it the TV first? Is it? I mean, yeah, that's a mess. That's crazy.
The stories.
The the cable power thing. One last question on that, and then I'll check to see if there's any questions from the viewers. But we talked about if we have a low a low problem, we add in the little amplifier. Maybe it's a little attachment on the end of the cable. Is it true for the opposite? So if I do have the little module plugged in, I get everything synced up and plugged in, and I get no picture. Maybe there's too much power, and I have to remove the little device or dongle that's on the end of the cable.
Are you talking about power or are you talking about signal?
Just the power part of it.
Okay, no. What the danger of the power part of it, and this is where there's danger, and we see this all the time. HDMI's got 5 volts coming out of the source, right?
Right.
So you got a Blu-ray player there. You plug it in. There's 5 volts coming out of that sucker, and that 5 volts has got to get to the sink. If it doesn't get to the display, it's not going to work.
Right.
And then it'll never turn on hot plug, right? So it's mandatory you get that right. Okay. It's 5 volts. Now there's a reason why it's 5 volts. It's because a 5-volt regulated supply is about as common as water coming out of the sky.
Yeah.
I mean, like, hello, 5 volts, right? That's
right.
why USB 5 volts. Everything is 5 volts, right?
Right.
As pretty much standard. Even though now, we're building some electronics now that's operating at 0.8. Really, really pretty cool, 0.8, yeah.
0.8, yeah, cool.
Yeah. So there's different supplies for chipsets, but for the average transmission line or power it's 5 volts. Now here's the problem with that. So that 5 volts has got to be regulated.
Yes.
It can't be dodgy around. Like, you can't go to 6 and down to 4.
Right.
It's got to be
right.
It's got to be rock solid at 5, right? So the source side puts a regulator around that, and they're not that big, small little chip regulators. They're not that expensive. Except the regulators are designed to put power or voltage out.
Right.
So in other words, it may take 7 volts in and regulate it down to 5.
Sure.
But then you got some clown that goes down to the TV set and says, "Oh, I'm going to add power."
Yeah.
So he puts on his little dongle power supply, and that dongle power supply is 6, not 5.
Yeah.
Well, the 6 goes backwards, doesn't it? It's going to go right up the wire, right back to the source.
Right.
And the little regulator there doesn't know that.
Mm-hmm.
And so depending on where that voltage is, it could very easily damage the regulator. And now
Yeah, it
you just
could.
destroyed the source. You
So,
know, and there's ways of fixing that. In fact, I know for a fact that on your inserters, they have protection for that.
okay.
But
Yeah.
many people don't do that.
Mm-hmm.
You know, I mean, and in this case, the bullet train product has those.
Mm-hmm.
They've got everything. I mean, they
Right.
pass into the metallic colors. So
Great.
they have that strength to them
Mm-hmm.
that so many people would like to have. It's just that they don't. You gotta work at it. You gotta get in there and get dirty, and many people don't. So
Is there a way, and I think this is probably the last question. Yep. Is there a way for an installer in the field to know when to avoid that to make sure that he doesn't blow up a source? Or is it just plug and pray? Anything you could think of?
Oh, I
I
mean,
mean,
for me, it's easy. I just go out there with a voltmeter.
yeah,
I
yeah,
would
yeah.
figure it out. But
Good.
for a guy in the field, there's nothing out there that will tell him. Well, there's a couple of devices out there because I made them for these guys, and what they
Yeah.
are is they're products that use an operational amplifier,
Mm-hmm.
and so it uses a differential, and what it does is it monitors what's coming out and what's going in.
Oh, cool.
And if the out is not matching the in, it corrects the overall out. Okay, so it's a differentiator. So it goes back and forth. It continually corrects itself. You don't see very many of those around.
Yeah.
And the thing that the installers have to know is chances are if they're not adding anything from the external world, it's going to
Mm-hmm.
probably be okay.
Yeah.
And the nice thing about the external world is that, remember I told you 5 volt is like water from the sky?
Sure, sure.
So for them to go out and get a 6 volt, which by the way, there are many of them, but for them to go out and get one, you got to work hard to get a 6 volt job.
Yeah.
But here's where the problem comes in: is one of those power supplies fails.
Yeah.
Remember the regulator, so they go down or they go up. So if the regulator fails and goes up,
Oof.
they're going to go up. They're going to go to 6, 7, 12 volts.
Right.
Say goodbye to your source.
I was gonna say, I
It's
should say,
over.
instead of saying oof, I should say poof.
Oof, right. And like in the old days, poof, you're a pile of S, right?
Yeah.
And that's what happens to it. And so the good companies, again, go back to what you guys do over there, right? The good companies, they look at those things. They listen to people like me. I'll suggest things like that, and
Right.
they won't just turn around and walk away. They'll handle it.
Mm-hmm.
And that's the difference between manufacturers. Some manufacturers, they don't give a crap. They just want to sell those things off. Other
Yeah.
manufacturers, man, they can be out in the field and stuff will get out there. They'll pull the stuff back if they have to.
Yeah.
So
Those are the ones I trust and I know are taking it very seriously.
oh yeah, and now with 48, with this envelope as big as it is,
Mm-hmm.
let me tell you, guys, you better do your homework and get the right product.
Yeah. Well, Jeff, that's great, man. Lots of awesome information. There were a few questions, and I think we got to them all.
Okay.
I know that you and I really want to do a session like this every so often. Maybe every month or 6 weeks or so. So I want to be able to answer some of the questions and concerns about not just HDMI 2.1, about HDMI in general. So instead of you and I could come up with topics all day, but I want to make sure that the people that are watching and listening and that are working in the field, they're getting the information that they want. So if you're watching this video, whether you're watching it right now live, or maybe you're watching the replay on YouTube, please guys, leave in the comments, what do you want to know? And we'll cater these sessions around you guys. We can Jeff can get very technical, or we don't have to get too technical at all. So you guys let us know what you want, and we will totally cater to what you guys are looking for. So, Jeff, thank you so much. That hour flew by. It's always a lot of fun. Yeah, we'll get together and start looking at the next session.
Oh yeah,
And
let's see if we can get the guys to write in what they want, because
yeah,
we
it would
have
be
all the
great.
answers. I mean, we just go through the database and make up a small presentation, and we can teach them.
You know what might be fun, and this is just maybe me, but you know, I like to geek out with stuff. I've done this my whole life, and I love instruments and tools and boxes with blinky lights on them. You know what I think might be interesting, and guys, again, leave the comment if you think this would be cool, but I would love to see like the stuff you're using to do this testing. I know you're using a probably very expensive oscilloscope and your test equipment. I think that'd be cool
Yeah.
just to see what it's all about.
We could do that one day. We could we
Yeah,
could we could do
yeah,
a camera right on the test equipment, and actually demonstrate how the tests are made.
yeah, that's awesome.
It's real easy to do that, and that may be
Cool.
a great idea.
Yeah,
And then we could actually take raw tables and say, okay, let's try this one. Let me show what happens here.
I like
And
that.
yeah, it's great. It's great. It's great. We can
Cool.
access management in there if we want to. So
Excellent.
yeah, send those letters in, and thank you again for the opportunity of being with you guys again.
Yeah,
And we'll set it up for another time, Jason.
awesome. Thanks, Jeff. And you guys reach out to me if you have any direct questions. And like I said, leave those comments. You can always email me directly at jason@murideo.com. I'm pretty easy to find. And Jeff, we'll see you next time. Thanks a bunch.
Bye bye.
Bye.